equilibrium, which is a measure of how much a reaction goes to completion. So when you start out reactants and you have these products, the truth is you don't have any products. This should be blank. And to the extent that you form product, your reactant has to diminish. This reactant's the only reactant goes to completion. And K is large, it means you get a lot of product. If you have a little tiny K, it means you don't get much. So first of all, we have the equilibrium constant. This is represented by KEQ, and it tells us to a liquid if they are soluble salts and they become something new. And so this measures how much new stuff do we get. It's calculated by products over the reactants. Literally, it's the product of the products raised to the power of the coefficient divided by the product of the reactants raised to the power of their coefficients as molar concentrations. If you can't remember who goes on top and bottom, this is alphabetical order P over R. This is called, therefore, a mass action expression because it includes both product and reactant. An example, if you have A plus 2B yield 3C plus 1D, now you see my arrow going back and forth. We don't say yield anymore. For equilibrium reactions, we say in equilibrium with. Here's a specific example, and we would set it up like this. Here's the product of the products, and can you see they're raised to the power of their coefficients? Do you see that? Here's the products, so the product of the products raised to the power of their coefficients. You'll notice they don't have parentheses around them. We use brackets while they're formulas. And we replace with parentheses when we put molar concentration in here to replace them. Divided by the product of the reactants. Here's the reactants on the bottom, and you see they're raised to their respective powers. So here's a real example. You have two sodiums plus a chlorine gas, Cl2, and you get 2 NaCl. The KEQ, or equilibrium expression, puts the product on top, raised to the power of the coefficient, divided by the product of the reactants. You see that they're raised to the power of their coefficient. So you would read this as KEQ equal, open your bracket, NaCl, close your bracket, to the second power, divided by, open your bracket, sodium, close your bracket, to the second power, open your bracket, Cl2, close your bracket, to the first power. They are raised to the power of their coefficients. Now, that setup is the law that you use to get the K. Then you would have to calculate it by putting in the molar concentrations of those substances. Right now we're just learning to set up the equilibrium expression. The second one that we can talk about, how much product do we get, is KSP. KSP stands for solubility product, and it's how much a salt comes apart. You're not making anything new. You're just putting a salt in water and seeing how much it's going to come apart. This is calculated by products only, so it's not a mass action expression. If we have a salt, so we have 2 A's and a B in one formula, you automatically get 2 A's every time this breaks up and 1 B. Here's a specific example, sodium sulfide. There's 2 sodiums in sodium sulfide because sodium is an alkali metal plus 1 combined with sulfur. Sulfide is -2, so it takes 2 sodiums to make this molecule neutral, Na2S. Can you see that every time it breaks up, does that make sense to you? You're going to get 2 sodiums and 1 sulfur. These are kind of easy in terms of the coefficients. So you got Na2S in equilibrium with 2Na plus 1S. Notice that these do not have anything to do with coefficients. They're gonna reappear here, but they are not used in calculating anything. So you have, we're only gonna use the products. So it's sodium raised to the second power because of this, and sulfur raised to the first power because of this. We've gone ahead and put their ionization state inside the brackets, but it has nothing to do with calculating. Comes apart. So it's represented by K sub A, K sub B, I think rather obviously for acids or bases. To the extent an acid or base comes apart determines its strength. If an acid comes apart and releases lots of hydrogen, it's a strong acid. If a base comes apart and releases lots of hydroxide, it's a strong base. It's calculated by products over reactants, P over R, so it is a mass action expression. We consider both products and reactants. So let's say we have an acid here, hydrogen attached to any acid, which really means it's attached to any negative ion, and it comes apart into hydrogen and a negative ion. Here's a specific example. HCl comes apart into hydrogen and a chloride ion. So we would put the product of the products, raise the power of the coefficients over the reactant, which is the acid. Now muriatic acid, or HCl, is probably not the best example because it actually is one of the few strong acids that comes apart completely. So I use this only as an example of how to set this up. Now let's look at a base. We have a base, which is any metal. Attached to the hydroxide ion, obviously it's going to come apart into a metal and the hydroxide ion. So here's a specific example. Again, probably not the best example in the world because sodium hydroxide is a very strong base and comes apart almost completely. But as an example of how to set up our law, we have sodium hydroxide, which will come apart into one sodium and one hydroxide. These numbers that represent the ionization state are not used in calculating. They are just carried through as the oxidation state of the ion. Comes apart, K sub B equal, open your bracket, Na plus 1, close your bracket to the first power because of this, times the hydroxide ion raised to the first power because of this, divided by the concentration of the original base. So KEQ and K sub A, K sub B are mass action expressions. Your calculation is a top and a bottom. How much a salt comes apart is just a product. That's because if you put something in water and it doesn't come apart very easily, there will be so much of the undissolved salt. If you're putting products over reactants, the reactant will be so big and the product will be so tiny, since it hardly came apart, the number is so small it becomes meaningless. So we just deal with the products in the case of the salt. So this, again, this whole area of equilibrium is how much a thing goes to the right or goes to completion. So things can become new things, how much are formed. A salt can come apart, how much, or acids and bases come apart, how much. So these are the three great areas of equilibrium. We're going to talk about KEQ and KSP first, and then probably in a 12th lecture address acids and bases just to keep them separate. But I want you to see that in many ways they are alike, although they are different. Much like labs, everything is alike, everything is different. They all are measures of how far it goes to completion. They all yield a number, K. If it's big, you get a lot of product. If it's small, you don't get much. And then beyond that, they become very idiosyncratic to whether they are a KEQ, a KSP, or a K sub A, K sub B. So you go ahead and get this down.